record this session. Here is me, and Manchester, as you will know by now. And I thank George in particular for inviting me to give this talk. And I didn't think very much about that, but in reality, it's an interesting thing, particularly in these times where the world seems to be dominated by eVTOLs. And it's easy to forget that eVTOLs are still not yet there. And this vehicles do amazing things day in and day out. See, what you see here is a Sikorsky S-64. I'm going to talk about this in a moment. It's a nice image I got from Getty Images there. It's against the sun, and it's an incredible machine. I'll show a few words now. So what we do is just to give you a general introduction to aerial firefighting. Of course, helicopters are not the only vehicles that are used for firefighting. There are also fixed wing vehicles. So just a few things about environmental hazards, operations, and then the new things are coming up. The fact that you can understand the operations of helicopters and any vehicle fitted with transponders. You can analyze their flight operations by looking at ADS-B data, whether these are from the ground or from space. And the CAMS is a satellite system that basically records atmospheric conditions, weather conditions all around the world. So I won't talk much about that, but ADS-B is one of the things we've done. So there are 3 case studies, and I'll show you some typical fire operations for a heavy lift helicopter, for a medium lift, and for a light helicopter. So I'll show you how we can identify the main aspects of the flight. Now, the thing is, the fires are generating I would say, a line of business that you wouldn't think about 50 years ago, and that's because the world is on fire, and you can get this from some internet sources. They use satellites, and this one is from NASA. NASA is a system called the FIRMS, and you can see it basically in real time almost how many big fires. So these are the big fires are shown on this map here. So wherever it is red, you can guess what's going on there. But the map as shown here is too big. You cannot see in much detail what's happening in many places. But if you look at it, I see the island of Madagascar is basically on fire. The east of Africa is basically on fire. The Amazon forest is on fire. The Northwest, the United States, and Canada is also on fire. It's something worrying. You can look at that yourself. India, China, actually Indonesia. Indonesia is not seen in here, but there is fires everywhere. Some of these fires are natural. There is really nothing we can do, and nothing actually we should do. Others are man-made, and they go just out of control. And especially when they reach inhabited areas, they become serious worries, as they have been in recent years in countries like Greece, like Portugal, like Italy, and so on. So something really to worry about. So, but I want to say that there are now this internet-based satellite systems that will let you look at almost real life fire. And if you zoom in, sorry, you can see the fires in Northwest North America. You can of course do this for any region you like. So this chart here shows fires which are active and the fires which are being controlled. And as I said, some of them are natural, and as they've been there before, civilization. So we really know about that because the body would venture in this, northern areas of British Columbia, Alberta, Saskatchewan, and so on. But other ones, particularly in California, Oregon, as you said, there are quite dangerous fires, the Los Angeles areas, and so on. So again, this is just a zoom in on some of the areas, and you can see where are the active areas. And I guess it won't be possible even if you wanted to extinguish all these fires. So priority would be given to fires that threaten, human activities. So everything is actually very complex and quite costly. And this is what I like to say. In Europe, we have another system called the FIS, so European Forest Fire Information System. There is a link in here if you want to look at it. It's actually quite a nice service they offer for free, and is run by the Copernicus program. The Copernicus program has been running for a number of years, and it's a lot of data there for anyone who wants to do atmospheric research or in this case a bit of flights. It's pretty good because you can get damage assessment for the ground, various statistics, data, and so on, the risks of fire, etc. So you can do some data pinging, other requests. There is other information you can look at that yourself, and they use data which come from satellite sensing. Flight data, of course, you could in principle get them, but often you can't because there is some confidentiality in there. So FDR, so this is a flight data recorder, is mostly unavailable because I hear the story over and over. There is a commercial confidentiality there. But even if they could do it, actually it is time consuming to get the FDR data out of the device. So this is what we call the black box. And then there is a DSP, as I said. So is basically using transponders on the aircraft. They're both ground-based and satellite-based. The ground-based systems are both commercial and free. A free database is called Open Sky. You can look at this Open Sky and see what kind of data you can get there. They're not very clean. There is a lot of work to do to get the data out of there. There is a commercial entity called the Flight Radar 24. And there is another one which is satellite-based. It's a company based in the United States. So the transponder doesn't transmit straight to the ground, but transmits to satellites. So there is a difference in this kind of data. Aeron are pretty good because they can cover also the oceans. We're not interested in the oceans, flight over the oceans in this case because we have helicopters and Flight Radar and Open Sky. So one important thing is that they offer data like ground speed, not the true airspeed. So if you want to do performance analysis, you need the true airspeed. This is not available. You need to find that from other sources. And I would say there are incredible photographs on the internet. Anybody who's interested in firefighting, particularly helicopters, they're just incredible pictures on the internet. And that shows, how important helicopters are day in and day out and what they're capable of doing. So fighting large fires, some of the fires I said that you don't actually fight because it's not worth it. But if you do have to fight them, then you got a response time, how quickly you're going to get on the site, and you need to manage the action. You need to manage people on board. You manage people on the ground, and so on. So as I said, because we have now, compared to many years ago, we have all these data services. So you can look at the size. You can look at trends, which sometimes it can be several hectares, square kilometers, I would say, that you need to handle. Then you have to look at atmospheric conditions, particularly winds are very important because winds tend to fan the fires and they make it worse. And temperatures usually is very high temperatures and they are compounded by the live flames and rain. Rain is useful obviously because it helps with the firefighting. The location is of course very important. It can be semi-remote or even remote that is not reachable any other way. There are no roads, or if there are roads, it may take hours to get there. Suburban is what we care about because there have been fires in suburban areas that actually have seriously damaged the houses and the urban infrastructures. So the fires can be anywhere. It can be on steep hills, it can be mountainsides, it can be on plateaus, and not all of them are easily reachable if there are no roads. Important also is the proximity of water. So once you got the fire, you want to fight for and extinguish the fire. Is there any water nearby? So it can be deep water, it can be shallow water, it can be the entire ocean, it can be a lake, a river. I'm not aware of rivers being used, but the importance of water is not to be discounted because obviously if there is no water nearby, then the vehicle has to come back to the airport and then try to refill at the airport somehow. So there are large bodies of water. These are good for particularly for fixed wing aircraft that they can refill whilst flying very low on water. Helicopter operations, of course, are very, very high risk. Is not a game to go out with a helicopter and fight fire. So of course there are emergencies, emergency situations. You deal with a difficult terrain, and complex operations. You're not going from A to B and then coming back. And I'll show you some examples of what these helicopters do. You have all loads are essentially sling loads. So you got to manage sling loads compared to internal loads. And of course, there'll be human factors. I'm not an expert in human factors, but I can imagine these helicopters flying for 3 hours or maybe for 6 hours in a day. You know how they can create enormous pressures on pilots and the people on the ground. Harsh environments all the time. So you have the smoke plumes. They affect visibility and, of course, orientation and the full control of the aircraft. You can have open flames. Sometimes the helicopter flies just over open flames, and these are incredible hazards to fly on. Important for the safety of the aircraft is the activity of the winds. So you need to understand where the winds are coming from, so that you can attack the fire from one direction or another. And the convective activities, if you have high convective activities, they go for those who do wakes analysis. The convective activities are opposite to the wake, so they change the behavior of the aerodynamic forces and loads on the main rotor. There are three main strategies to attack these fires. One is direct, so you basically drop retardant over live flames. Retardant is a mixture of water with a chemical. Sometimes if there is no chemical in there, so it's just water. And there are problems with the water, but you do what you can with the resources you have. So you in this case, in the direct attack, you just throw water over live flames. In the indirect attack, you do what you can to prevent the further expansion of the fire. So the fire is going to expand downhill or uphill or whatever. So you put a line of basically a desert in front of the fire, so it cannot the front cannot move any further. And finally, there is a parallel attack. If you have an edge of the fire which is long along the line, so you try to cut through the line through a parallel attack. So there are three ways of doing this, and of course this has to be established. The strategy is to be established depending on the fire, and every fire is actually different. So important to say that these helicopters are all converted from military applications, from transport, from cargo. I'm not aware of a single rotorcraft being designed explicitly for firefighting. So if there is a surplus from military fleets, there is likely to become a rotorcraft for firefighting. Of course, you have to go through a number of obstacles, which include recertification. If you convert it to a different application, so it costs a bit of effort, engineering efforts, and of course financial cost to do that, but it's cheaper than designing a new rotorcraft from scratch. So military surplus, transport, and cargo, they do 100% of the firefighting. There are three types of helicopters. They are given here as a Type 1, Type 2, and Type 3. The Type 1 is the biggest, and it basically includes aircraft like Sikorsky SS-64, as we mentioned before, the Chinook CH-47, and they have a bucket or an external load capable of about 10,000 liters. So 10,000 liters is basically almost 10 tons, 10 metric tons. So it's a lot of water there. And once you have the water, you need to know how to drop it. You're not going to drop it just quickly in a single space. So the Sikorsky can take up to 15 personnel plus evacuees if you need to evacuate people, although not all at the same time. The crew is made of 3 personnel. There will be a pilot, there will be a co-pilot, and there will be a fire operator. They need deep water resources. Actually, this is not always true. Perhaps I can correct that. They not always need the deep water resources. If they have a hose, the hose can operate within a meter of depth. So even if shallow water, I think I've seen helicopters operating over shallow waters. So they can be fitted with a hose. I'll show you a picture in a moment. So they can be fitted in a minute. The tank is filled in less than a minute, and the tank is deployed in less than 3 seconds if you absolutely need to drop everything in a quick sequence. This is a real helicopter for firefighting over great fires. Type 2 is a medium helicopter. So the examples here given are the Bell UH-1 SBUE, also the Bell 412, but these are actually quite well used, particularly in North America, and they load the buckets of not up to 10,000 liters, because that goes way beyond what these helicopters can carry, but the order of 1,200, maybe 1,500, then 2,000 liters, and so on. So firefighter personnel can be up to 9. So some people can be dropped nearby and operate from the ground, and they do initial response to wildfires. So once the alarm has been given, they are the first to go there to wildfires. Type 3 finally is the light helicopters. An example given here is the Bell 206 Jet Ranger. So I'll show you some tracks of this one here. So it can load buckets of about 1,500 liters. So it can be both water bucket and the internal tanks, which can be deployed in a matter of a few seconds. So overall, the fleet that is around the world, this is around the world. There's not any particular organization. There is all this aircraft here. So they got the Jet Ranger, as I said, the Bell 212, the 412, the Cobra AH-1C, which is again is a military surplus. The SBUE is a military surplus. The Sky Crane, actually this is not 46, it's 64. Sorry for the typo. And said the Chinook. In Europe, but also in North America, there is the Airbus Eurocopter AS350 EcoRay that has been renamed a few times. For these types here, there are flight data available and the fire available. We have them, so we have analyzed quite a few of them. I know there is also the Boeing MD-500D operating as a firefighting vehicle. There is a Common K-MAX, which is very good in hover performance, and then there are Russian helicopters, of which I don't know anything, I have to say. And the one I know that has been fitted as a firefighting helicopter is the Kamov 32. So recent developments include the drone applications. Now I have to be clear here that drone applications are very different from the helicopters you've seen. They've been proposed for fighting urban fires, for example, in high-rise buildings. And in the case of forest fires, they're very useful for detection, for monitoring, for remote sensing before you actually send the real aircraft, to fight there. So it's good to have a detection, nearby that you can see in much more details rather than using satellite images. However, they're too small to tackle major fires, and I don't see this situation changing for the next several years. But the technology is rapid advancement. They can certainly fight, urban fires, whether there are up in high-rise buildings or in areas which are not accessible. The drone applications are out there. However, I have to say that they will cover, say, a market, so to speak, which is different from the likes of Sikorsky 64. So many rotorcraft, as I said, are released from military service. They are aircraft which have maybe thousands of hours of service on the airframe. They are updated. They are certified for firefighting, and the certification is not an easy thing to do, as you well know. And because there is a considerable amount of upgrade and delivery systems. And I would say in a recent magazine of, I think is a magazine, I can't remember what is the name of this magazine, there is a lot of on firefighting technology. It's mostly about the filling systems and the deployment systems. So the historical context is very easy. So there's been basically these aircraft have been using water buckets, and these buckets are called Bambi buckets. So they be both rigid and flexible. So they require costly supplementary type certificate, and these buckets are fitted to all types of helicopters from Type 1 to Type 3, and they can be bought effectively commercially. So the operational flight data have been increasing. Actually, I forgot to say that now there are GPS tagged vehicles and also water tanks, and they track all the drops efficiency, the number of drops, the flight characteristics, and so on. So because GPS has now become so accurate, you can see, being if you tag a bucket, you can tell, what they have achieved by a single drop. Although we can see this in part from the flight tracks. So there are various techniques to drop the water or the retardant. So the bucket is refilled on the ground with water or mixed with retardant. So you have four situations here. One is a wet drop. They call it wet drop when the sling load is dropped straight onto the live flames. Then there is a spot drop. So in this case, the sling load is kept at a certain height from the fire, and therefore there is a bit of fragmentation of the water droplets. So the area which is basically affected by the water drop is larger. I mean, it's not shown in this picture, but will be larger. The stitch drop is when the aircraft is actually flying forward and releasing the water a bit at a time. And finally is the hook drop, where the sling load is basically swinging left and right and trying to cover as much as possible over the fire area. And I made here a nice drawing, but these are serious situations. For fire retardants, I'm not going to speak about this because there are chemicals. Each of them is different for basically effectiveness, and there are papers just on the fire retardants, and there is one paper in here that I'm just citing, and as I say, is a separate subject, so I won't be covering that. Going to the flight data and the fire data, as I said, that there are historical data available. They can be plotted on maps like Google Earth and so on. Flight data, as I said, they've been used for this research, but we have all the data, OpenSky and so on. It is important to have a registration number on the aircraft, because once you have a registration number, you can go back and look for the right files, which once they have been extracted from the database, they become basically CSV files. So it's comma separated files which are opened by just the spreadsheets. So it should be easy. They are converted to KML files. KML files can be loaded by Google Earth, so you can take basically the tracks from the origin, say Flight Radar 24, and plot them directly on Google Earth. I'm going to give you some examples of this. So the actual firefighting mission contains aircraft position compared against historical wildfires. To do a search, you need to do a seasonal search. Mostly this happens in the summer. Luckily we don't have fires at this time of the year. And normally arrival departure for this aircraft is the same place. So they depart from an airport, they come back to the same airport. They're not going to stay elsewhere. It's not always the case, but generally, aircraft go back to the same airport. So what do we have here? So the flight data are analyzed. They're inferred from the SCV files. So we have the origin airport, region or arrival airport. You can infer number of missions, number of water drops, the flight duration, the flight speed, the altitude, the height from the ground, and you can do an estimate of the cost of the drop. So this is a bit tricky to do because each country is different. The cost of operating this aircraft is different, but you can guess what it costs to drop, say, 1,000 liters of retardant on a fire. So each mission, as I said, is different. Each fire is different, and each of them could make a test case. So let me start with a few test cases. This is a Sikorsky 64 Sky Crane. This is owned by the Italian Fire Brigade. It's an amazing, rotorcraft, I have to say. And when it was this summer, and I landed at Ciampino Airport in Rome. There were two of this part. One was like this. Of course, I didn't take the registration, and the other one was painted green. And I was so amazed that for a moment, I must admit, for a moment, my breathing stopped. You just got to see this aircraft to understand what is rotorcraft technology out there. And this is a monster, and it's just an incredible machine which has probably 70 years of lifespan, and they're still out there. So a huge rotor of 7 blades, 22-meter diameter, and the maximum takeoff weight of the order of 19 to 20 ton, and the power, almost 7,000 kilowatt. So this is what is being used in recent years, at least in Italy. Of course, now there are sort of a cooperation between the different countries to actually lend some assets when there is one serious critical fire in one country or another. So I want to describe one incident. We've done a few. So I take this one, which is a fire in San Gabriel Mountains in California. There is a date there. The origin is Laverne. Laverne is a town in Los Angeles County. And we've seen that this aircraft has done 15 round trips from a water reservoir to wildfire front, there and back, with a drop of about 150,000 liters over this mission. This is incredible. So a climb up to 700 feet per minute, up to 3,500 feet, where it was the height of the fire, because the town or let's say the reservoir was 650 feet. So you had to do this climb up every time it did the cycle, and then climb down. So it could decelerate to hover in less than 15 seconds, which is amazing considering the size of the vehicle. And when you plot this KML files onto the map, you find things like this. So you have a region here. So there is Laverne down here. There at the bottom right. So there is a scale here, which is nautical mass, 10 nautical mass. So there is also the direction of north. So the fire is shown in here. So this is a SC-64 typical mission. So this fire is called Popcat fire. Each fire it comes with a name. Particularly in America, they give it a name to each of the fires. So the yellow lines, which you can distinguish very, very little here in this case, is the operations of the aircraft. We estimated that the water drop, where the water drop is occurred, and the water refill. So you can zoom here on the map. In fact, I'll show you in a better detail, which is this one here. So the aircraft will go down here at the bottom of this page. You see this blue dot. There are two reservoirs, and I think this is drinking water as far as I can tell. And the aircraft fills with a hose, and then it flies to the fire. I mean, to the edge of the fire, drops the water or retardant, and then it comes back. And you can see there is a back and forth in there, except in a couple of instances, it's actually hovering and then flying above the fire. The reason for this is unclear. It's also unclear why it is going out here. Okay, no, it's coming from Laverne, which I think is to the east of this reservoir. So it's coming there as a refuel, and then going back to base. So we can plot this differently. So we can look, for example, at the speed and altitude. So this is the easy way to plot the data without going into details of the aeromechanics. And you can even almost count the operations here from the bottom line. So where you have the altitude, you see that the aircraft is coming down 1, 2, 3, 4, 5, 15 times at the altitude there, and then going up to deploy the load up to 3,500 feet several times. And I think at least a couple of times he's deploying the load at the lower altitude, maybe 2,500 feet. And of course, there is a speed. The speed, goes down almost to zero, and it is when the aircraft is loading its tank. Of course, you can do a lot more from this. You can infer, for example, average climb rate, average descent rates, and many other things that can be done just from this simple track. The second case is the Bell UH-1. This is a Super U. This is a fire again in California. It's a fire in Susanville Mountains, again in North America. The date is again, you can read it yourself. And this aircraft did, according to what we found out, 26 round trips from water reservoir to the fire front. We don't know how much drop was done. Probably, the operators would know that, but we all inferred this from the data tracks. So this is, of course, a medium lift helicopter. The trip to the fire was only 3 minutes. So this shows, how quickly you can respond to a fire. And climb was only 500 feet because there was not much difference in height between the fire and the water reservoir. But we see that the acceleration to hover from speed took place in about 10 seconds or less. And this is the way it happened. So what you see here on the right is this town called Susanville. There is an airfield, the minor airfield, and it comes straight out of there, and then it goes, is the previous case, loads into a reservoir. It's not shown very well, but you can see better, the kind of trips that goes from the fire to reservoir and back. And I can zoom in, and I zoom in, and I find what happens in reality. Okay, so it goes back and forth, and this colored area is the area of the fire. So you can see that the area of the fire is quite extensive. Is not something very easy to tackle. And I guess now you can ask yourself why was the water dropped there in the middle of the fire? Of course, we've not investigated this. It would be interesting to know. It's not obviously part of helicopter operations. It would be part of their own strategy for attacking the fire. Or alternatively, you could think about, attacking the parallel to the fire, just here, roughly at the center of the picture. But this is a really demanding operation. It took about 3 hours. Okay, and this is the track. Again, you see altitude and speed. Not much difference in altitude and speed between maybe 4,000 and 4,500 feet. Not much climb or descent, but there is a lot of change in speed. All the way from maybe 90 knots to hover. The aircraft is doing this speed change several times, and you can see from this really jagged curve. So this is case study 3, although it says 2, is a Bell 206B Jet Ranger. So this is again another fire. Sorry, I should say this is not in Susanville. I've done this very, very quick. This is around Van Nuys. Van Nuys again is in Northern California. Van Nuys is an interesting airport because Van Nuys is, I think, is the busiest general aviation airport in the United States. And they have about 250,000 operations of general aviation. And I would guess that includes also operations like firefighting. So in this case, the Bell 206 did 11 round trips from water reservoir to wildfire front. We don't know how much drop it did, but it was able to go to the fire in 4 to 5 minutes from the reservoir and climb up to 500 feet as the previous one. So it's quite agile sort of aircraft. And this is plotted here. So it went from Van Nuys. Van Nuys is actually a very interesting airport. So you can find this on Google Earth Pro, where it is. It's a fairly big and busy airport. See now is on the bottom left of the page. Is over here, okay. And then it does this big trip and back and forth between the fire and the water load. So here is I guess the reservoir, and then the blue is where the water is actually dropped. So if I were to zoom a bit, so this is what happens. So we are in highly urbanized areas. So this fire is actually threatening, property. So there was a case of emergency. So you see the flight paths, you see the water drop, and this is the refill of the water according to what analysis we have been doing. So this is the flight pattern, like in the other cases. So the altitude and the speed the speed up to 90 knots and the altitude, 2,000 feet or just above, and you can count very easily, the number of drops from the altitude, the drops and the refilling from these changes in altitude. Okay, so obviously, it takes longer to load bigger tanks. And so you got the filling time here. So we looked at what it takes to load one of these tanks. And of course, as you increase the tank capacity up to 10,000 liters, you get up to maybe 2.5 minutes for each of this water tanks. Okay, so a few notes on performance. So the analysis of data can be done for, say, for example, time on the ground, the time for refueling, the climb descent rates, as I said, times between drops, number of drops, number of missions in a day, and the total flight time. In fact, sometimes this aircraft can fly up to 12 hours a day in situations which are really, really critical. And this will lead me to, say, a summary or a conclusion where area firefighting offers clearly superiority. I didn't talk about the fixed wing. Fixed wing is another thing, is another area which we need talking about, but we'll leave it for tonight. So we look at speed, areas impossible to reach by road, and there is no other way to extinguish the fire but from the air. Missions of a single asset last up to 3 hours because this is what the endurance of many helicopters is, 3 hours, maybe 3.5. Consider there is a lot of accelerations, decelerations, climb and hover. So, we are pushing to last 3 hours. But they also have the advantage to, turn around rapidly, fly precisely onto the fire, something that the fixed wing aircraft cannot do. So recent progress from our point of view is the ability to examine in the flight planning, the maneuvers, all the data that are available from the aircraft, also from the satellite and from remote sensing. So there is a massive amount of data can be harvested, and all this can be used for, of course, for improving the operation's effectiveness. The drawbacks, of course, are risks to pilot's life due to the rain, the hot plumes, and extremely complex logistics and training required to fight these fires. And I said before, human factors. I'm not an expert in human factors, but I imagine these operations have been extremely stressful. And I concluded with one of the photos I found on the internet, which is helicopters save lives every day. And I'm proud to say that, yes, this is what they do. This is one of those Bell helicopters with a Bambi bucket dropping straight onto very, very high, very serious live flames. And with this, I will conclude my talk, and I will be happy to take some questions if there is the audience is having any question.